Hello, my name is Eduardo Lopez. This project is for CS6263. The title of my project is A New Approach to Smartphone Authentication. It is based on the original paper, ABC, Enabling Smartphone Authentication with Built-in Camera. The authors of the original research paper are as follows. From University at Buffalo, State University of New York, Zhangji Ba, Sixu Piao, Demetrius Koutsanakis, Kai Ren. From University of Central Florida, Xinwen Fu and Aziz Mohisen. The contents that will be covered over this presentation are ordered as such: introduction, background, system model, threat model, problem, design goals, proposed system, performance, and usability. Keywords. Over the course of the next couple of slides, I'm going to go over some keywords that will help the listener understand the presentation a little easier. Some background information is when an amount of light falls on a sensor in a digital camera, the camera, in theory, should output exactly the same voltage. However, due to imperfections during the manufacturing of these sensors, when the light is shined in the cells output slightly different voltages. This difference is what is called PRNU, photo response non-uniformity. Fingerprint or fingerprinting. No, it is not the digit on your hand. You could think of fingerprint or fingerprinting as sort of like clues. They are signs that uniquely identify something. The next several slides will give a brief introduction to what is covered in the original research paper. Introduction. Identifying and authenticating smartphones is now a massive part of our daily lives. Federal Reserve statistics state 53% of users in America use their phones for mobile banking. 28% use their phones for mobile payments. This number continues to grow. As this number grows, it leads to greater opportunities for cyber criminals. In return, there is a bigger need now than ever for multi-factor authentication systems. These systems need to specifically focus on device security along with the security of the user. There are many ways to secure a smartphone. The way that we will be speaking about is the ability to use a phone's built-in sensors for security. Fingerprints are what make sensors unique. Each sensor leaves its own fingerprint. Each device has its own unique fingerprints per device. So if you have 10 iPhones, each iPhone would have its own specific signature for each sensor. Photo response non-uniformity, or PRNU. PRNU is used by digital forensics teams to track down criminals when all they have are pictures or a camera. Given an image, they may identify the suspect by correlating the image's noise residue against the camera's fingerprints. From previously in this presentation, I described a little more detail what PRNU is, but just to recap, PRNU is when the light enters the sensor on a camera, and because of defects from when the sensor was made, the light gives off a specific fingerprint. And so they are able to, the forensics teams are able to take that fingerprint and correlate it to a fingerprint or residue from a picture and match them up. This presentation will explore the use of PRNU from a smartphone's camera sensor to identify and authenticate a user's device while also defeating various frauds and attacks. There are a few challenges with using PRNU for mobile security. The overhead is huge. Conventional cameras require at least 50 pictures to acquire a usable fingerprint. That is a massive amount of data and extremely impractical to have to use 50 pictures. PRNU is also susceptible to fingerprint forgery. A bad guy could take a victim's smartphone's pictures. They could hack them and get the pictures and take the fingerprints off those pictures and embed them into their own image. And they could use that to bypass PRNU. Current forgery detection for PRNU has high overhead, which we will discuss further on in the presentation, and it is not very reliable. The original writers of this paper conducted research comparing smartphone cameras to conventional digital cameras. The first thing they noticed was the smartphone's image sensor is incredibly smaller compared to the digital cameras. The smartphone's imperfections of their sensors are the same as a conventional digital camera. Because the image sensor is smaller in a mobile phone, it amplifies the pixel dimensions and creates a very strong PRNU. The writer's research results show that PRNU is so strong that only a single image can uniquely identify a smartphone camera, whereas from a conventional camera, 50 images were needed. This lowers overhead incredibly. The writers suggest by using PRNU from the noise residue of an image, they can use that as a reference fingerprint, meaning they can take a picture that a phone has captured and take the noise residue off that and compare it in order to figure out which phone took that picture. And previously, they needed 50 images to make that happen with a conventional sized camera. But using a sensor in a cell phone, you only need one picture. The writers propose ABC, a PRNU-based smartphone authentication protocol. Golgin proved that fingerprints coming from cameras have incredibly high accuracy and low false positives. 1 million images were taken by 6,896 individual cameras. The false rejection rate was less than 2.38%. The false acceptance rate was below 0.002% in conventional cameras. Fingerprint forgery attack and countermeasures. Fingerprint forgery attack could be done by someone with malicious intent who wanted to fabricate forged images. There are two current forgery detection methods. The first is the fragile fingerprint method. This method requires 300 raw images. 300 is a lot. The triangle test method. In this method, in order to detect fingerprint forgery, you would need to have every image that the smartphone has ever captured. And due to social media and the way technology is today, that is nearly impossible. System model. There are three pieces in the ABC protocol: the user, the smartphone, and the verifier. The user will use the smartphone to transmit to the verifier. This goes through a wireless channel. It can be Bluetooth, NFC, Wi-Fi. VLC is visible light communication. They are not directly communicating with each other through VLC. However, the means of light that is compared back and forth is what is considered the VLC channel. What happens during the ABC protocol is after the user has registered their picture, the verifier will post two QR codes. The user will take a picture of the two QR codes, and in doing so, in the image that the user took will have a fingerprint on it for that phone. And they will then upload the pictures to the verifier, and the verifier will check the QR codes for the correct fingerprint and data inside the QR code. We will go more in depth into this further in the presentation. Threat model. The writers created a threat model to assume the worst case scenario by a powerful adversary, and they wanted to make sure that their protocol could defeat this. The first potential attack they are planning to defend against is a malicious user who may want to make a payment with the victim's bank account. They may use a replay attack or fingerprint forgery. The second attack is a malicious merchant who wants to lure the victim to authorize a malicious payment, also known as a man-in-the-middle attack. Design goals. The writers have three design goals for the ABC protocol. The first of which is attack resilience. They want to use only fresh images. This would help with their security. And they want the ability to detect forged images. They would like to use real-time authentication so that their security prevents against people using photographs from outside a specific time window. And they want their protocol to be user-friendly. They want the verifier and the user to have low overhead, which means not use very much bandwidth, be quick, and be efficient. In the proposed system, the users were only able to make the ABC protocol work because the smartphone sensor is smaller than the traditional camera sensor. The writers conducted their own study using 16,000 images with 40 different phones to once again prove that the noise residue correlates to a very specific phone. The small pixels exhibit strong non-uniformity. This is what creates a high-quality fingerprint in a captured image. The writer's system was tested indoors. This is the worst possible scenario. The system is based off the intensity of light. Low light doesn't make it impossible. It still works very well. It just works even better with more ambient light. In their research study, they used two types of image pairs: matching on the same phone and non-matching, taken with different phones. The writers' study used iPhone 6s and Galaxy Note 5s. They had 1,250 matching pictures for the iPhone 6 and 1,150 non-matching pictures. The Galaxy Note 5 had 4,000 matching pictures and 5,300 non-matching. Quick definition, the peak to correlation energy. It is the measure of similarity for two discrete signals. In figure 2, taken from the writer's original research paper. You can see that in A, it shows the matching image pairs captured by the iPhone 6. The higher the PCE number, the more the frequencies from the fingerprints matched. As you can see in figure B, the non-matching pairs captured by the iPhone 6 had a pretty much 0 PCE value, which means they did not match at all. The writer's research results showed that the iPhone 6 had a false positive rate at 0.08% and a false negative rate at 0.71%. For the Galaxy Note 5, they concluded a false positive rate of 0.16% and a false negative rate of 0.94%. This showed that the ABC protocol was incredibly accurate. It only used a single image versus the 50 images that a conventional camera would have needed. The research was conducted indoors, which was the worst case scenario because their system is based off light. And it showed that it has a very low overhead. The overhead is because it only required one picture, and the 50 pictures is just a massive strain on a mobile device. The writer's ABC protocol consists of two-phase authentication. The first of which, the registration phase, is when the user uploads a fingerprint profile for the target phone. That gives the verifier a fingerprint of the user's phone. The verifier would then store that data. In the authentication phase, the verifier presents two QR codes, which are used for real-time authentication. QR code, also known as quick response code. It is a vital piece of the ABC protocol. It contains 3 pieces of information: an abstract of the ongoing transaction. The user can view this by decoding the QR code. It contains a probe signal, and it contains a timestamp. The timestamp is used so that the QR code cannot be used outside of the time window. The abstract defeats the man-in-the-middle attack because the user can verify that what the transaction is, and that will thwart any man-in-the-middle attack. The verifier is able to perform image content and fingerprint matching. They do this by comparing the noise residue to the reference fingerprint that the user first uploaded during the registration phase. But what is the probe signal for? The ABC protocol still needs a way to prevent malicious forgery. There are 2 main forgery detection methods that we will speak about. The fragile fingerprint method. The fragile fingerprint method requires 300 raw images. Raw images are very big. This means there will be an extreme data burden on both the user and the verifier. This creates a high overhead. The second method is the triangle test. The triangle test tests all available candidate images that may be available to the adversary. This means you would need every single image that the user has ever created with their phone as reference. Due to social media and how much the average smartphone user uploads their photos, this would be nearly impossible. Not to mention the overhead would be incredibly high. The amount of data you would need to transmit all of these images, the storage space, it would put a huge burden on the verifier. And this also creates privacy issues. The user may not want all of their pictures, every single one of them, to be known by the verifier. But we still haven't mentioned the probe signal. In fingerprint forgery, a fingerprint can be removed with a denoising filter. The adversary can easily do this. But probe signal to the rescue. A probe signal, a white Gaussian noise, is inserted into the QR code. The probe signal can survive photographing, but it will not survive fingerprint removal. This white Gaussian noise, or probe signal, is checked by the verifier when the user uploads the picture of the QR code. If somebody with malicious intent tried to remove the fingerprint from the user's photo, the white Gaussian noise would not survive, and the verifier would be able to mark the uploaded picture as malicious. The following are the official steps to the writer's proposed ABC protocol. Step 0. The user uploads an image on account creation to establish a fingerprint with the verifier. Step 1. The verifier generates 2 different QR codes. Step 2. The user verifies the abstract transaction. They can do that from actually reading the QR codes and making sure that the transaction is what they are intending to do. They capture the codes by taking a picture and upload the captured pictures to the verifier. Step 3. The verifier receives the codes and performs analysis. The analysis consists of image content matching, making sure both of the QR codes are the same codes that they presented. Fingerprint matching, they want to correlate the fingerprints from the pictures and the camera. Forgery detection, they want to make sure that nobody edited the QR codes. They could do this by comparing the PCE values. And they want to make sure that the signature from the photograph was not removed, and that is where the handy dandy signal probe comes in. The writers conducted research to test the performance of their proposed system. They used 6,000 images captured by 30 iPhone 6 devices. They used 10,000 images captured by 10 Galaxy Note 5 devices. The resolution of the images were 2248 by 3264 and 2048 by 1152. The images collected were from Amazon Mechanical Turk and the writer's devices. The images published on Amazon Mechanical Turk had no limitation on image content and time frame to ensure randomness. The writers used PCE to measure correlation between residue and reference fingerprint. The impact of age. The average smartphone user's phone lasts about 22 months. The writers evaluated smartphones' PRNU with images from 2015 to 2017. That's 3 years. Over the course of 3 years, the PRNU value did not change, not even the slightest. Impact of ambient light. There were 6 settings that the writers tested the impact of ambient light. Indoor low, windowless room with dim lamps. Indoor median, windowless room with several lamps. Indoor high, several windows. The outdoor settings were all done on a sunny day with the sun out. There were 3: the outdoor morning, outdoor noon, and outdoor evening. The strength of the fingerprint on a captured image is increased greatly with the rise of ambient light. They proved that the outdoor scenery carries a stronger fingerprint. This leads the writers to show that if the verifier wants to use the system and get the highest results, they could just add light to their system. Or they could just use the system outside. The writers also tested in their experiment temperature and humidity. They tested indoors with a fixed light. The temperatures were 17.78 Fahrenheit, 45.5 Fahrenheit, and 85.1 Fahrenheit. The humidity numbers were 27%, 45%, and 78%. They recorded no difference to PRNU under any of these circumstances. Image resolution. PNG versus JPG. They are the most common image formats. PNG wins against JPG in every comparison except for non-matching pairs. Interpolation methods, nearest neighbor, bilinear, and bicubic, were used to compress. They also crop the images in order to make the image sizes smaller. The writers conducted another experiment to test usability. There were 40 participants, 20 male and 20 female. The age range was between 21 and 54. The participants were randomly picked. The participants were given a 1-minute introduction to the ABC protocol system. There were 2 Galaxy Note 5 devices used, 1 user and 1 verifier. 95% thought photographing phase was efficient and comfortable. Figure 3 shows the time to complete. You can see by looking at Figure 3 that the average time to complete was about 4.2 seconds for the whole process, start to finish to end. Conclusion. Smartphone cameras demonstrate very strong PRNU. This is because the sensors in smartphones are very small compared to conventional cameras. The manufactured defects in each sensor create a much stronger PRNU. The writers designed ABC to be attack resilient in real time. It's a user-friendly smartphone authentication protocol. It differentiates phones using PRNU. Smartphone registration only requires a single image. This is compared to a conventional image registration, which would require 50 images. The experiments conducted prove the results of the ABC protocol, and the results prove low error rate with high success. References. Reference 1. The original paper. The original paper goes much more in depth than the presentation. It has algorithms that I did not put in the presentation that, if you would like to read, are there. Number 2, the original writers created their own PowerPoint for this presentation. It is extremely good. It is more descriptive with pictures. I was not going to take their pictures and put it in my PowerPoint. I did use 2 of the pictures from their original paper, but not from their PowerPoint. Reference number 3, PCE. That is where I got the definition for PCE from. Number 4, PRNU. That is where in the beginning of the presentation I gave the definition for the keyword PRNU. I hope you enjoyed the presentation, and thank you for your time.